Alright, welcome to our next video. This one's called gas laws. This is where we actually look at the quantitative relationship between the four different actual properties we talked about in our first video. So, when dealing with gases, we have many different relationships that we can actually observe between their pressure, their temperature, their volume, and their amount. As a reminder, pressure is denoted by P, temperature T, volume V, and amount N. And typically that will be ATM. Not always though. Temperature is always Kelvin. Volume is liters or milliliters. And N is mole. So, let's look at these relationships. These relationships are observed to be true regardless of the situation, so we call them scientific laws. And since they're dealing with gases, we refer to them as our gas laws. Anytime I use the phrase gas laws, I'm going to be referring to these 3.5 gas laws. So, the first gas law deals with the relationship between pressure and volume, and we call it Boyle's law. So after a guy named Robert Boyle. And it states that as pressure increases, so pressure goes up, volume will decrease if kept at the same temperature. Okay? Or we often think of this as volume decreases, pressure will increase. Okay? So that means that, I'm going to try a different stylus real quick. I don't think it'll work. But let's say you've got a big box and you've got a lot of dots. Okay? If you decrease that to a smaller box with the same, or even if you smaller, you get them a lot more concentrated, and it ends up being higher pressure, basically, if you will. That's what Boyle's law is stating. So, in equation, this is P1V1 equals P2V2, where P1 and V1 represent our starting pressure and volume of a gas. P2V2 represent the final pressure and volume. I'll give you a secret. It actually doesn't matter which one you use. You don't have to have the starting here or the ending here. In fact, there's often not even a starting or ending that's obvious. So just make sure that typically the types of problems you're about to see will be, we have a pressure and volume here. We change the pressure, what's our volume? Or we change our volume, what's our pressure? Just make sure that your pressures and volumes are matched up with basically the sequence of the problem. Let me give you an example. So, a sample of oxygen gas has a volume of 150 ml at a pressure of 0.947 atm. What will the volume of gas be at a pressure of 790 torr if the temperature remains constant? So, we're dealing with pressure and volume. So I'm going to start by writing P1, V1, P2, V2. It doesn't really matter which one is 1 and 2, just pair them up correctly. So we have 150 mil, at 0.947 atm. And we have, we're not sure, and our new pressure is 790 torr. And we're looking for a new volume. Alright, so here's the thing. We could have put these as our P1, P2, and V2. Doesn't matter, just keep them paired together. So, when we look at our pressure, one's in ATM, one's in torr. You got to pick one of those units. So either put them both to torr or both to ATM. Typically, I recommend just going to ATM. That's kind of what you're going to be used to doing. But if you really like torr, then I recommend everything goes to torr. It's really up to you. I don't really care. ATM's definitely the easiest, but it's up to you. And as for volume, if they give you in milliliters, put your answer in milliliters. If they give you liters, put your answer in liters. If they give you both, pick one. Okay? So, I'm going to convert this to ATM. When I do that, I get 1.04 ATM. So, our equation is P1 V1 P I'm going back and forth between two styluses. One's really slow and sucks, and one's really not slow and sucks. Probably shouldn't have used the phrase sucks. And I use it again. Whatever. So, that gets, when you plug in things, you will get 0.947 ATM times 150 equals 1.04 times V2. Use a little bit of math, and your final volume will be 136.6, which should make sense that if we increase our pressure a little bit, our volume will decrease a little bit. Alright, there you go. That's Boyle's Law. Most of the gas laws are about this straightforward. So if you're stuck in this, ask questions. If not, let's move on. So the second gas law deals with the relationship between volume and temperature. It's called Charles' Law. Basically states that as temperature increases, the volume's also going to increase as long as the pressure stays the same. So that says that if you've got so many particles and you heat it up with some fire, they're going to start moving faster, and your pressure is going to initially decrease or increase. They're going to start pushing. Okay, that's weird. They're going to start pushing harder because they're all warmer. That means to reduce that, pressure, you have to put a bigger space. That way, yeah, they're moving, but the pressure is a little bit smaller. So that means that as your temperature increases, they're going to take up more space, and thus you're going to have to increase your volume if you want to keep your pressure the same. Okay? So, this is our equation. V1 over T1 equals V2 over T2. V1 and T1 are the starting volume and temperature. V2 and T2 are the final volume and temperature. As with Boyle's, it doesn't really matter. Just make sure that your, whatever temperature goes with your volume 1 is in T1. It can be in, if that happens to be your second volume, then your temperature is now your second temperature. Just keep things paired up together. Okay, sample of helium gas occupies 2.5 liters at 300 Kelvin. The balloon is cooled to STP. What's the new volume? So they mainly tell us volume and temperature. We're assuming the actual pressure staying the same. Typically they'll mention that, but we're just going to assume that's what happens. So we've got V1 is equal to 2.5 liters. T1 is equal to 300 Kelvin. V2 we're solving for. And they cool to STP, which hopefully you remember occurs at a temperature of 273 Kelvin. Stylus is really not good. I have a better one at school. I'm actually at my house. I left my stylus there. Okay, so let's plug things in. We got V1 over T1 equals V2 1 over T2. Sorry. I got a new stylus. I was hoping this will work better. I was wrong. Whatever. So that gets you to... It's even worse. 2.5 over 300 is equal to V2 over 273. Okay, you're going to be doing some cross multiplying. Final answer will be 2.28 liters. So we are decreasing our temperature by a little bit, so our volume should also decrease a little bit. So there you go. That's Charles' law. Okay. Third law deals with the relationship between pressure and temperature. It's called Gay-Lussac's law. It's very oddly uncommon. I'm not too sure why, but this is called a few other things. I was taught as Gay-Lussac, so there you go. All right, this law states that as temperature increases, pressure will also increase as volume is held constant. This means that if we have a box with, gas and let's say our temperature, is kind of pushing out a bit. If we heat that up, now we're going to have, in the same size box, we're going to have larger pressure, because they're going to be moving around and hit the wall at a harder speed, thus higher pressure. So, in equation, P1 over T1 equals P2 over T2, and you know what those variables mean. I'm not going to tell you again. So, there you go. Alright, so at 122 degrees Celsius, pressure of a sample is 1.07 atm. What will the pressure be at 300 degrees Celsius? So, we have our P1 is 1.07 atm. Our T1 equals 122 degrees Celsius. We're looking for our P2, and our T2 is 300 degrees Celsius. Hopefully you remember that we need to actually convert these to Kelvin. So if you already solved this and you didn't, well, fix that. When you get these to Kelvin, though, you get 395 Kelvin and 573 Kelvin. So our equation is P1 over T1 equals P2 over T2. If we plug in our values, we get 1.07 over 395 is equal to P2 over 573. I'm pausing it because that way I've got more time to get my stylus to work. Anyways, do some more cross multiplying, and our final answer is 1.55 atm. There you go. If you did not convert this to Celsius and you got a different answer, yes, I will mark you wrong. You always have to go to Kelvin. There is no exception. There you go, though. That's Charles's law. I'm sorry, Gay-Lussac's law. Okay. Final law basically combines everything together, and this is the law that most of the time you're going to be using. Notice you can see every law in there. You've got Boyle's law, you've got Charles's law, and you've got Gay-Lussac's law. So let's practice using it. Alright, if a gas at 1 atm, 475 Kelvin, and occupies a volume of 2.4 liters, what will the volume be when the pressure is doubled and the temperature is decreased to 375 Kelvin? Well, we set this up the same as we've been doing. So our P1 is 1 atm, volume is 2.4 liters, T1 is 475 Kelvin. They say our pressure is doubled, so that means it's now 2 atm. We're looking for our volume, and our temperature got decreased to 375 Kelvin. So if we plug that into our equation, we get a very, very scary kind of ish looking equation. Here's our formula, by the way. Okay, and again, as usual, do some cross multiplying work, solve a bit. Your final answer is 0.95 liters, which should make sense because we're doubling our pressure and we're cooling it down. So it should be quite a bit smaller. But that's combined gas law. It's the same as the others. It just has more stuff in it. However, you can use all the gas laws from this. So if they ever say temperature is constant, just cross out the T's. If they ever say volume's constant, cross out the V's, and now you've got whatever other law you need. There you go, though. That's combined gas law, and those are our gas laws. Thanks for watching.